Good evening, everyone. Am I audible? Can anyone from the participant reply me?
Yes, sir, you are
Yes,
audible.
sir. Yes, sir. Audible.
Okay. Thank you. Welcome all again for day 4 of the Atal FDP on deep learning, intelligent video analytics, and computer vision. So, with the day 4 starting with the core topics of object detection on videos and a use case of video analytics in intelligent transport system. Those are the sessions today. So I would like to welcome back our resource person, Dr. Hasan Firdaus sir, and I would like to hand over the session without wasting any much time. Dr. Hasan,
Yep.
you can
All right.
start the session, sir.
Sure. All right. Thank you, Mr. Chairperson, Dr. Afsar Baik M. All right. So, thank you. Assalamualaikum warahmatullahi wabarakatuh, and very good evening. Okay. Very good night if you are in Kuala Lumpur. Okay. Good evening. Possibly in India. All right. So, yeah. So this is already day 4 of the program. Okay. Of this online faculty development program. So how are you guys doing? Okay, so we are in Kuala Lumpur. We are having a heavy rain now. Now it is raining very heavily. All right, so it's quite chilly. All right, so yeah, hopefully you all guys are also chilling. All right, and still in high spirit to continue to our sessions. Okay, so let me share my slide and then we can start directly. All right, so let me share entire screen. All right, hopefully you can already see my slides. Okay. All right, so it looks like there are several participants still keep coming in. So it's okay. Probably we just start the intro. Okay, so to this session, okay, like previous sessions as well, although I didn't follow all of the sessions, but to this session, now I will be delivering the session in a hybrid mode. So hybrid mode meaning that I will start a little bit on the theoretical introduction, okay, the background of the topics, and then we'll go to the hands-on part. Okay, all right. So the title that have been given to me is the object detection. All right. So let's see. So we are now in our day 4 of the program. Okay, so today also we will be covering about the use case of this video analytics in transport system or robotics. Okay, so will be covered by other speakers. All right. So let's start introduction on the definition of object detection first. Okay, so I'm understood. I've been told that previous sessions covered on the image classification. All right, yeah, if I'm mistaken. So if I'm wrong, please correct me. So perhaps this is the type of network that have been introduced in the earlier sessions. All right, so this is what we call as CNN. Okay, convolutional neural network. So I think the previous sessions in I think this one, all right, introduction to PyTorch for the classification, okay, as well as the transfer learning, should already cover this. Okay, so where, all right, just to revisit the image classification. So this is what the network of classification will do. All right, so it will take the input. All right, in our case, the input is an image. All right, so let's say we have an image or a set of images of a car, right? And we want the network to learn, right? To learn how to recognize a car, right? So what we will do, we will use this as input to our network, okay, and then pass through to this deep network. So that's why we call it deep learning. So deep network consisting of several layers, okay, multiple layers. For example, here we have a layer of convolution plus ReLU. Perhaps other speakers have already covered that. I won't go into detail. All right. So followed by the second layer, which is pooling. All right, and then we have again we have the convolution and ReLU layer. All right, and then followed by pooling again. So these two layers, okay, these two operations will be repeated several times. So for example, if we take the example of LXNet, for example, so this operation will be repeated 5 times, okay, and then what it will do towards the end, it will have some what we call as classification layer. All right, classification layers where we have some fully connected layers, okay, where at the end it will try to predict, okay, the image, okay, based on how many classes that we have at hand, okay. So for example, we have let's say we have 10 classes, okay. So let me change to a pen, okay. So let's say we have 10 classes: car, truck, van, dot dot dot, bicycle. So let's say bicycle is the 10th class, sorry, okay, class number 10. All right, so towards the end we will produce the some probability, right? So let's say some probability, for example here, yeah, because it is probability, so the prediction at the end here, all the values here will be summed to 1, okay, so the total will be 1. So for example, let's say our prediction of car is 0.7, for example, right? And then trucks, for example 0.001, for example, and so on, okay, but the total is equals to 1, okay. So what classification will do is for one input image, okay, it will try to predict, okay, it will try to predict one we will try to predict one label, okay. So based on this list of probabilities, it will take the highest one, okay. For example, the car here is 0.7, which is the highest compared to other classes, okay. So it will choose car as the class for this image, right? Okay, so this is what we call as classification. So classification, we have one input, okay, and then we will be outputting one output, okay, which is the class label, okay. In this context, it is a car. All right. All right. So how this is different from detection, okay. So if we say that classification is trying to recognize, trying to give a label to the whole image, okay. So let's say this is the whole image, consisting of a cat, okay. It will give one label to the entire image, okay. So this image is cat, okay. Where is the cat? That's not the concept of classification. All right. So but the entire image contains a cat. All right. So that's the classification. All right. So for the next, we have what we call as localization. Okay, localization. So what is localization? Is when we know the position of an object. Okay. So let's say this is the entire image. So let me change to the laser pointer again. Okay. So let's say this is the entire image. All right. So we know the location of the object. Okay. So that's what we call as localization. So that location is denoted by bounding box. Okay, so this is what we call as bounding box. Okay, a box that closely locate where the object is, from in the image. Okay. All right. So if we actually combine these two, all right. So classification, where we have the label, and the localization, okay, where the location of the object in the image. So that's what we call as object detection. Okay, so where object detection give us not only label, okay, but the location of the object in the image. Okay, so for example here, the dog bounded by this blue box. Okay, so that blue things denotes the label of the dog. Okay, and then the cat is classified, or is located using the bounding box colored by, okay, while the dog is in the green. Okay, so that's the difference that we need to understand first. Okay. Right, so this is an example of object detection that we are looking at. Okay, so we have the entire scene of the image. We want to locate the object, all the objects in the scene. Okay, and we want to also classify that object. So, for example, person, laptop, and so on. Okay, so that's actually the beauty of deep learning. All right, so the exact same network. Okay, you give exactly the same input. For example, here the image of Ronaldo. Okay, so it can do several things. Okay, so for example, it can do the classification, and then where we will give label to this image, and it can do what we call as regression as well. All right, so regression where in this context, okay, if we want to detect the nose tip of Ronaldo, we need to regress the location of the nose tip. Okay, this task will involve prediction of the X and Y location of the nose tip. Okay, so that's where the object detection actually starts. Okay, so as I said, so we have an image like this. Okay, so we will have two things. Okay, so we will have bounding box. Okay, we will have class. Okay, so the next thing that we need to know, okay, the other information that the object detection will give us is this thing. Okay, if you can see here at the left hand side. Okay, so a bounding box, okay, this bounding box colored red here is given by these four values. Okay, well, what are those? All right, so so we have X, Y, W, and H. What are those? Okay, so this is X and Y here. All right, is the location. Okay, is the location of the bounding box where normally it is the top left of the bounding box. Okay, so here. All right, so this is the coordinate. Okay, the coordinate of the top left of the bounding box. So this is X and Y. Okay, all right, so this is a standard in many models, in many algorithms use the same convention. Okay, all right, so you will be given the coordinate of the top left of the bounding box, and you will be given this another two values, okay, which is W and H. So what is W? So W is the width, okay, and H is the height. Okay, so where is the width? So this is the width, okay, and we also have the height. All right. So meaning that we have four information that we need to know so that we can draw a bounding box. Okay, without this four, it's not possible to have our bounding box. Okay, some algorithm probably they won't use these four values. All right, instead the other alternative is to use not to use W and H, okay, but to use another coordinate. All right, so normally the coordinate that will be used is the top left. All right, and the second one is the bottom right. If the top left is denoted by xy and x1 y1, okay, the bottom left will be denoted by x2 y2. Okay, so still we will be having four values as well. All right, so x1 y1, x2 y2. All right, so it depends on how the algorithm was trained. Okay, we'll see after this. We will try one of the examples of object detectors. Okay, afterwards, you can either use WH or X2 or Y2. Okay, we'll see after this when we do the hands-on. Okay, just a little bit brief history. Object detection has been there quite long back. Okay. All right, so it starts, of course, by the image processing techniques. Okay, so for example, start with the what we call as a Kenny detector. Okay, to detect, to detect the blob or the line or the edges of the objects. Okay. All right, and then in 2001, okay, 2001 is the first, successful object detector has been proposed. Okay, so what we call as Viola and Jones. Okay, still people are using it. Okay, due to its quick implementation. Okay, all right. So of course, Viola and Jones use a technique or features called half features. Okay, so this is one of the handcrafted features in image processing. Okay, where it actually calculates the gradient of the image. We won't go into detail on that. Okay, and then 2005. Okay, 2005, where the second one, which is quite popular at those times, well before the deep learning era comes. Okay, histogram of oriented gradients. Okay, so also it will calculate the gradients of the image, okay, in the x and y direction, and then it will locate this in the several bins of histogram. Okay, and then use that as a features of the objects. Okay, and then comes the era of deep learning. All right, so LXNet, where this thing I have already discussed in our first session. Okay, where in 2012, okay, comes a modern family of convolutional neural network. Okay, proposed by this Alex and team. Okay, and they call it LXNet. Okay, so this is where the image classification first time in history to to be able to outperform the human performance in image classification. Okay, but the problem arise. Okay, the problem arise at that time, several 12 or 13 years ago, because the LXNet can only do the classification. Okay, classification in the sense that when we give one image, it can only give us one label. Okay, but it cannot do detection. All right, so at those time, okay, the researchers at that time, scratched their head to, to answer the research question, or how to actually transfer this LXNet, okay, to be able to use it for image detection. So that was the research question at those time, okay. And then of course the straightforward the direct transfer from the LXNet, of course, we can do something like this. All right. So, for example, we can define a a filter, okay, like a window, for example, in this blue colored window, okay, and we can extract this, and we can use this. We can give this as the input to our LXNet, for example, okay, and try to classify, right? To classify at the end, for example, whether there is any person or not, or face. Okay, so let's say we want to detect a face, we want to do a face detection. Okay, so it will, you know, it will slide this uh, filter. It will slide the filter to sorry, I'm trying to change my pen color. Okay, all right, so let's say we start here. Okay, give it as input to our LXNet, and then try to classify whether, okay, this is face or not a face. Okay, and then go to the next location. Okay, where we slide the filter, and then try to classify again. Okay, and then do that to the entire image, up from the top left to the bottom right. Okay, and then try to classify. Okay, so this is like a brute force way to directly transfer LSNet from classification to detection. All right, so but can you see, can you already see the problem? Okay, of course, because we need to do the brute force searching of the face in this image. Okay, and this can involve, most probably hundreds of thousands or even million patches. Okay, million filters that we want to fit to our LXNet. All right, so this will of course incur lots of computational complexities. Okay, where I still remember at those time, this brute force techniques, will take some 4 to 5 minutes to run a single image for the detection. Okay, so it's really inefficient. Okay, and really resource hungry. Okay, so it took 2 years. Okay, from 2012 to 2014 to actually come up with a technique to transfer the LXNet to the detection task. Okay, what we call as RCNN. Okay, still a very popular model nowadays. Okay, all right. So that which stands for region-based CNN. Right. So region-based CNN. Okay, the method is still the same, but at the first stage, it will use some algorithm to randomly take several patches. Okay, but still all these patches will be given to the CNN. Okay, for example, LXNet. Okay, to classify one by one. Okay, which is still not very efficient and very slow. Very slow. Even if you run on GPU, it's very, very slow. All right. So, and then comes 2016. Okay, 2016 is the year that starts the revolution in the object detectors. Okay, so where comes a technique that is called YOLO. Okay, have you come across this name? Probably yes, because it's already a popular model nowadays. Okay, so YOLO, what YOLO stands for? All right, so yeah, probably you only live one. All right, so in this context, for the computer vision, okay, it's not you only live once, but you only look once. Okay, so instead we need to slide our patches throughout the image and then classify. You For using YOLO, you can just pass the image one time, okay, and then directly get the results or the prediction at the end. All right, so that's why it's called you only look once. Okay, so or some people call it single stage detector. Okay, so where you just need to do the single pass of the image through the object through the model to do the object detection. All right. Okay, so this is an example of another single shot detector called SSD. Okay, SSD stands for single shot detectors as well. Okay, so this was proposed at the same time as YOLO, 2016. Okay, as well. So what it did, just pass the image one time. So let's say this is our image. Okay, pass through the network one time, and then instead of we need to go through the patches one by one. So just feed this once, and then let the different convolutional layers predict for our bounding box and class. So that's how they use this to predict some multi-scale detections of the objects. Okay, so if you try to actually compare those models, okay, RSNN, okay, of course, after RSNN, we have fast RSNN a year later, and then we have faster RSNN, okay, still in the family of RSNN. Okay, so if you try to plot the accuracy versus speed of those model, okay, so probably you will get something like this. Okay, so what does it mean? Okay, so it this one denotes that, for example, the faster RSNN for example can give you the highest accuracy. Okay, the highest accuracy here. Okay, at the expense of low speed. Okay, so this is the speed of the RSNN. Okay, whereas for the YOLO, for example, let's take YOLO. Okay, the accuracy is somewhere like this. Okay, but we can have a very efficient implementation. Okay, so the speed is significantly higher compared to the RSNN family. Okay, so that's why if you are talking about the implementation in industry as well. Okay, of course, YOLO and SSD is a go-to models to use for the real application. Okay, because normally for the real time applications, okay, we speed is a must. Okay, speed is a must. Although we probably can sacrifice the accuracy a little bit, but of course this accuracy can be remedied by several techniques. For example, how do the way you get your data and how you train the model. We'll see into more details on how to do that afterwards. All right. Okay, some other information that we need to also discuss regarding the object detection, okay, is the performance metrics. Okay, so here I will give some overview of the object detection first, because after this, when we try to train the model, okay, we will see this term, okay, about this performance metrics. Okay, that we will need. That's why we need to discuss it beforehand. Okay, all right. So, how the object detection performance been evaluated? Okay, so it is evaluated in two ways. Okay, in two matrices. Okay, first is the classification. The second one is the localization. So of course the classification uh, as covered by other speakers. Okay, so this one is evaluated using what we call as uh, accuracy. Okay, so but how do we evaluate the localization? Okay, so that's what we want to discuss now. All right, so we want to know how accurate the location is. All right. Okay, so this is the things. Okay, so all right, so we have two matrices. Okay, classification and localization. So in object detection, however, we for the classification metric we don't use the accuracy. Okay, instead we use what we call as MAP. Okay, which denote the mean average precision. Okay, mean average precision. Uh, is it? We will discuss after this. Okay. So and the second matrix is the localization metric. Okay. So where we will be using the IOU. Okay. Which stands for intersection over union. Okay. Okay, let's discuss IOU first. Okay, intersection over union. So let's say you have the label or what we call as ground truth of the bounding box in green. In green, the box is in green. Okay, let's say our model prediction is the red colored box. Okay, so the predicted as well as the ground truth. Okay, based on this, we can actually get the Okay, actually we can get the value of the intersection over union. Okay, which is the value between 0 and 1. Okay, how do we get those values? Okay, so this is how we get the values. All right, so if our prediction, if our predicted bounding box is exactly the same location as the ground truth, okay, meaning that the x and y, okay, the top left position and the width and height is exactly the same, prediction and the ground truth, we will be having the IOU equals to 1, meaning the perfect match of the prediction and the true label. Okay. However, if we have some overlap, okay, so let's say our prediction have some overlap of the ground truths in this region. Okay. So, and the overlap is 0.4 or 40%, okay, of the ground truth area, okay, pixels. Okay, so we will be having IOU equals to 0.4. Okay, so let's say our prediction is totally out of range. Okay, so with no overlap to the ground truth at all. Okay, so we'll be having the IOU equals to 0. Okay, so that's how we actually define our intersection over union. Okay, or IOU. Hopefully that's clear. All right. Yeah, mathematically, of course, IOU not only the intersection, so it is the area of intersection
Vada Vandi.
divided by the area of union. Okay. Okay. So now let's move on to the average precision. Okay. So I've told that we have two matrices. So one is IOU, the other is MAP. Okay. So now let's discuss on the MAP. So MAP, which stands for mean average precision, come from this average precision. Okay, where to understand the average precision, of course, we will need to understand these three things first. Okay, so the first one is the what we call as confusion matrix. Okay, the second one is the precision. Okay, the third one is the recall. Okay, which are using from all of this, we will define our average precision at the end. Okay. All right. So what is confusion matrix? Okay. So I'm sure that some of you are familiar with this. Okay. So this one just to as an introduction for those who haven't seen this before. All right. So in the to get the confusion matrix, we need to plot, okay, between the predicted, okay, our prediction versus the true, versus the true level. Okay, prediction versus true level. Okay, so and then in our matrix here, we can define four things. Okay, we can define four conditions. Okay, these four. All right, first is true positive, second is false positive, the third is false negative, and the fourth one is true negative. Okay, so of course, the true negative, as I put it here, okay, corresponds to not predicting a bounding box. Okay, no bounding box at all. Okay, normally usually a background. Okay, so because of that, it will not be used for the matrix calculation, because no bounding box. Okay, so and it is background, so we don't include that in our performance metrics. So we will what we want to see is these things. Okay, so true positive. Okay, if you predict the positive, meaning you say the bounding box is there. Okay, and it is correct. Okay, the bounding box is correctly say, okay, it is a car. Okay, and the bounding box is there. Okay, so this is the true positive. Okay, and then we have the second one is false positive. Okay, where you predict positive and it's false. Okay, in our object detection, meaning that you say that there is a bounding box. Okay, but it's not correct. Okay, okay, so that's a false positive. Positive mean you say it is there. Okay, but it's not there. All right, so it's false positive. All right, so we have the false negative. Okay, so you predicted negative. Okay, you say, okay, there is no bounding box in this image, for example, and it is false. Okay, the correct is there is a bounding box. Okay, so these three things will define our next metrics. Okay, so what we call as precision and recall. Okay, so what is precision? Okay, so precision is the actual positives out of the total positive predictions. Okay, so how many we say that it is positive, how many we say there is bounding box. Okay, and it is actually a bounding box. Okay, so what we take the true positive and divided by the total of true positive plus the false positive. Okay, and we also have the recall. Okay, what we call as recall. Okay, where we try to predict the actual positives out of all predictions. Okay, so we take the entire predictions, which is given by true positive plus false negative. Okay, and then we take the actual positive, so which is the true positives, divided by the total of the predictions. Okay, so these two will give us average precision. Okay, where average precision is the where you try to plot the precision and recall. Okay, where the average precision is given by the area under the curve of this graph. Okay, so for one class, okay, for one object, it is called average precision. Okay, so if we have multiple objects, okay, if we want to do the multi-object detection, okay, so we call it mean average precision. Okay, we take the average precision of all classes, and then we take the mean of the average precision. We will get the MAP at the end. Okay, so hopefully that's clear for the performance metrics. So in conclusion, we have two matrices for the to evaluate the performance of an object detector. First is the IOU, okay, and the second one is the MAP. All right, where we will see this again when we train the model. Okay, so before we continue, just want to see if everyone is doing well. All right, so please put your comment in the chat box if you have any problem. Okay, in understanding, probably I went too fast or too quick. Okay, so probably you can tell me so that I can adjust. Okay, there's a question for video analytics. Making use of YOLO will be visible, okay? Or is there any other model that can be used, especially traffic sign detection and recognition? Okay, all right. Sorry, my earpod suddenly jumped. Okay, all right. Yeah, sure. Okay, I will answer this question later when we do the actual thing. Okay, all right. So let's directly dive into the hands-on part. Okay, if you let me stop my presentation a little bit. Okay, all right. Before we dive into the hands-on part, okay, because we will be using this session and the tomorrow session as well for the object detection. Okay, because we have several things to cover. Okay, before we start, just want to see whether you have already installed the Anaconda and Visual Studio Code that I mentioned in our first session. Okay, so because why I'm asking this, because we will be using this in our session now. Okay, so if you still don't have the tool yet, okay, the Anaconda and the VS Code. Okay, so let me share again my screen. Okay, so when if you want to try this at home after this, you can install this by directly Google, Anaconda. Okay, all right, so this is the first one. Okay, Anaconda. Or if you don't have if you want to save the storage okay, of your computer or your laptop, you can probably use Miniconda, the mini version of the Anaconda. So anyone should suffice. Okay, all right, the second one is the VS Code. Okay, so VS Code is the Visual Studio Code. Yep, this one. This one. So you can go directly here and try to download and install on your machine. Okay, those are free softwares. We only introduce free softwares in this program in the hope that you can directly utilize it for your use case after this. Okay, that can be beneficial for your projects and for your research and so on. Okay, all right, so these two things is a must. Okay, Anaconda, again, Anaconda is the Python package. That is not a Python package. It's a software that for the machine learning or the data science. Okay, but of course it has the pre-built built-in Python. Okay, and the VS Code, the Visual Studio Code, is used as the environment or the IDE, what we call it as IDE for the Python. okay, that we will be using. Okay, so let's directly go to the what we want to do now. Okay, so if you have Anaconda in your machine, okay, all right, I will start from there, right? So you just go to your start, okay. This is assuming that you are using Windows. If you are using other machines such as Mac and Linux, still the same, but probably just the way you open the software, and probably how you there's a slight change in the syntax and so on, okay, but in normal case it will also you know it also can run on other machines. Okay, so if you have Anaconda, you can directly uh, invoke this Anaconda on your start button. Okay, start and then go to Anaconda. So you will have this Anaconda prompt. Okay, Anaconda prompt, Anaconda 3. Okay, so you just click that. Probably by the way, can you see clearly my screen? Just want to make sure. Is it okay? All right, I can see thumbs up. Okay, all right. So you will see something like this. Okay, so the base and C uses Hasan and so on. What do you do? What we want to do first? Okay, we want to actually start by creating our virtual environment in this Anaconda. All right. Why we want to do that? Okay, because we want to make sure that whatever we install after this, we will be installing several packages and tools and softwares. We want to make sure that all of this installation, okay, of the packages will only be done in this virtual environment, okay, without sacrificing our our main system, okay, for example, our C and our Windows and so on. Okay, so now let's start by creating the virtual environment. Okay, so I think I also include that in our slide. Okay, so yeah, we'll go to that after this. Okay, let's do the virtual environment first. Okay, if you have the Anaconda, you can define, you can create your virtual environment by writing this conda. Okay, Anaconda always start with conda or pip. Okay, all right, so Anaconda, so create. Okay, create, because we want to create the virtual environment. Dash dash, okay, double dash, name, sorry, name. Okay, conda create dash dash name, and then we give the name of our virtual environment. So this up to you. Okay, well, what the name you want to put? Probably I put this as what, Atal, for example. Okay, conda create dash dash name Atal. Okay, and then we can put also the exact Python version that we want to use. Okay, let's say I want to use 3.8, for example. Okay, if I'm not mistaken, Python, the latest version is already at 3.12 or something. Okay, so you can put anything. So 3.5. Okay, so let's say I want to put it 3.8. Okay, and then you can directly enter. Okay, enter. When you enter, you will be creating the virtual environment. Okay, where we will be doing all our codes inside this virtual environment starting from now. Okay. All right. So this may take several minutes, depending on your internet. Okay. So if proceed, yes, just yes. Okay. So it will installing several packages. Okay. This shouldn't take too long. Okay, but why I want to start with this because I want to show the correct way of starting a project. Okay, so let's say you have several projects. You can start with the virtual environment. Okay, let's say you have project 1, project 2, project 3. So you can segregate or segment your different projects based on different virtual environment, so that one environment won't disturb or have conflict with the other environment. Okay, so mine is already successful. Okay, so you say here to activate our environment, we can just write this. Okay, conda activate and the name. Okay, which the name I choose Atal. Okay, so conda activate Atal. Okay, enter. So when I enter, you can see here at the left hand side. Okay, at the left hand side, before this it says base. Okay, so now it has changed to Atal. Okay, or whatever name that you want to use for your virtual environment. Okay, if the name has changed, then we can confirm that okay, it's already in our virtual environment. Okay, where we will be doing all the installations afterwards inside this virtual environment without disturbing our main system. Okay. All right. What's next? We want to do. Okay. When we have the virtual environment. Okay. What we want to do next is okay. That one I will cover after this. What we want to do now is we want to create a folder that we will be dumping all our codes, and all our images, our data inside that folder. All right. So let's create a new folder. Okay. So I have created in my system here. You can create at any location in your system. Okay, in my case I choose D. Okay, you can see at the top here this PC D. Okay, and then I have a folder named codes. Okay, inside these codes I have several folders, right? So what I want to do is I create a new one. Okay, name Atal. So this one I just put a random name. Our program. Okay. And I have put several images and videos here that I can use this as test videos and test images. Okay, so I want to go to this folder inside my Anaconda prom, right? So if you want to go to here, you can just go to the tab at the top and then just copy the path. Okay, just copy the path, and then in our Anaconda prom you can just because we are now in our Anaconda prom is in C. If you see here, C users Hasan, right? If you want to go to D, you can just write D first, D, and then colon, the double dot, right? The colon, and then we will be going to the D. Okay, and then we can go to the directory or the path that we have copied just now by stating this. Okay, CD, and then we can paste our path there. Okay, so CD stands for change directory. Okay, change directory, and we just paste our absolute path to this Anaconda prom. Okay, and then if I click enter, okay, so now we are exactly inside this Atal folder. Okay, which we have this test images and test videos. Okay, and we will be running all our codes inside this folder from now on. Okay. If you have any problem following, just tell me. Okay, I will try to repeat again. Okay. Otherwise, the recorded video will be.
Excuse me, sir.
Yeah, yeah.
Sir, any code what you will be running, you will be sharing that, sir, so that we can also run here.
For this one, yeah, I already have in my
Because
PowerPoint.
right now I'm
If you
also
can.
in the same directory in the Atal
Okay.
itself. Exactly,
Okay.
I'm following.
Okay. Sure. Sure. Sure.
Yes, sir.
Okay.
Yes.
Yep.
Yeah.
All right. Thank you. Okay. So now, what we want to do now is we want to go to our. Oh, sorry. We want to actually install several things here. Okay. All right. So leave the Anaconda prompt first. Okay. What we want to do now is we want to go to the YOLO web page. Okay. So YOLO is hosted by Ultralytics. Sorry, Ultralytics. Okay. So you can Google Ultralytics. Okay. How I make this bigger? Okay. All right. You can Google this Ultralytics. Okay. So the first one. Okay. The first one you can directly go to the Ultralytics there. Okay. Probably not this. Okay, sorry. It is the documentation. So Ultralytics, I think this one. Sorry. Yep, this one. Yeah. So you should go to this Ultralytics YOLO 11. Okay, click that. You will go. You will be directed to this documentation page. Okay, docs.ultralytics. Okay. Okay, so YOLO since the first version in 2016 has now evolved. Okay, have lots of its variants. Okay, so now the latest one is YOLO 11, the one that we will be covering in this session. Okay, all right. So YOLO 11. Okay, as you can see here is the latest iteration in the YOLO series of real-time object detectors. Okay, so you can see here lah. Okay, so the MAP versus the latency. Okay, so you can say that 11 is the the highest MAP and also one of the quickest model as well lah. Okay, so we want to use this. Okay, so yeah, you can of course you can scroll this page by yourself and try to explore more. Okay. All right, so let's go to the quick start. Quick start. Okay, so now I'm in the quick start page. Okay, so install Ultralytics. So this is what we want to do now. Okay, so you can see here we can install it using pip install Ultralytics. Okay, so just copy or probably just click it here, copy to clipboard, and then go to our Anaconda prompt and just paste it. Okay, control. Oh no, what's happened? Okay, so just probably I need to okay, like this, copy, and then sorry, okay, and then just paste it in the Anaconda prompt, and then just hit enter. Okay, so it will download all the necessary tools and packages of the YOLO. Okay, from this Ultralytics. It may take some time depending on the system as well as the network, the internet. Okay, so yeah, this is the reality of AI developer and AI practitioner. So this is what you are doing. So this is what I want to show you, the real way of how you run the AI. Okay, for object detection. Okay. Okay, so while waiting for this to finish. Okay, let us go to the next part. Okay, so if you scroll this quick start page, okay, so of course first it says you can install by using this pip install Ultralytics. Okay, so the second one is although in the Ultralytics it will install the PyTorch. Okay, this one I have mentioned in our first session that we will be using PyTorch. Okay, so although Ultralytics, when we run this, okay, mine is already finished. Okay, although there is also PyTorch. If you see here, there is Torch. Okay, this one. Okay, Torch Vision. Although we have those, it is not GPU version. Okay, it is not GPU version. So how do you want to have the PyTorch GPU that can be run on GPU? Okay, so we need to go to the PyTorch. So just go to your Google Chrome again, or whatever browser that you have. You can go to the pytorch.org. Okay, pytorch.org. So you will go to this page. Okay, get started. Just quickly scroll down. You will see this thing. You will see this snippet. Okay, so where you can install the PyTorch on your machine. Okay, so depending on your machine, so just click stable. In my case, I'm using Windows. Okay, and you can, because we are using Anaconda, you can also either choose Conda or pip. Okay, the language, of course, we want to use Python and CUDA 11.8. Okay. Honestly, I haven't tried this 12.1 and 12.4 yet. Okay, but let's try this 11.8. Okay, so you can just copy this command and paste it in our Anaconda prompt. Okay, so you can if you want to quickly paste it, you can directly click your right click. Okay, you can put right click. Okay, and then just enter. Okay, enter. It will install. Okay, it will install the GPU version of PyTorch. Okay, why do we need GPU? Of course, we can just run on CPU. Okay, but we want to run on GPU because as I said before, deep learning models are resource hungry. Okay, resource hungry. So it will run also in CPU, but it will be very slow. Okay, because the model is quite big. Okay. Okay, so right now I will install. Okay, right now it will install all the packages. Okay, while we are waiting this to finish. Okay, let it run. Let it run. Probably take 1 or 2 minutes. Okay, let's go to the next part. Okay, let's go to the next part where we want to set up our VS Code. It's actually finished early. Okay, okay. So if we want to confirm that the installation of PyTorch is successful, we can try it by invoking this command Python. Okay, so we will say here Python. So I'm using Python 3.8.20. Okay, so you can directly like import torch. Okay, so if there is no error, okay, so if we run this and there is no error, meaning it is successful. Okay, so meaning that we already have PyTorch in our machine, in our system. Okay, so we can also check if there is any GPU. So torch, this one I cannot remember the GPU, but we will see after this if we have the GPU version. Okay, so we can exit this Python. Okay, like this. Okay, And then what we want to do next is we want to run the YOLO, okay, on our machine, okay, where we want to run on our VS Code, VS Code. So as I told before, we will be using VS Code as our Python IDE. Okay, so yeah, so if you have installed VS Code, okay, like this, you will be
Sir,
having this slide.
our packages are still getting installed, sir.
Yeah. Okay. All right. That's
Little bit,
okay.
sir.
That's okay.
Little pause, sir. A little 1 or 2 minutes.
Okay. Okay. Sure. Okay.
Yes.
Sure.
Sorry to interrupt. I
Okay.
request the participants to make a note of the points because we are time constrained.
Okay.
Because our resource person is running the systems on their GPU, our systems may not be able to cope up with the process. So I request all the participants, please make the note of the points and try it at your own discretions. Thank you.
Okay.
One more thing, if you are installing it first time, the download file may take a few hours also. Okay, so already on sir's PC, maybe the repository is downloaded. That's why it got installed quickly. Okay, please
Okay.
make a note.
All right. Thank you, Dr. Ahmad Rimas. Okay. Yeah. As the doctor has mentioned, so probably I just show first. Okay, and then after this, you can try by yourself at home. Okay. All right. So this is the VS Code that we have installed, that I have installed on my machines. So you should have the same, interface. Okay. Okay. So what we want to do is, okay, just probably, okay, we want to drag our folder here. Okay, we want to drag our folder that we have created just now. For example, in my case, Atal, you want to drag to our VS Code. Okay, so just click and drag it to our VS Code here. Okay, so that we are running our code inside this folder. Okay, so for example, if we want to do a new file, so let's say we want to do, let's say, test.py. Okay, so why.py? Because we are coding our code in Python. Okay, so that's why it's .py. Okay, so test.py, for example. Okay, so we can run our code inside here. So for example, import torch and so on. Okay, afterwards we'll see. Okay, the next thing that is also important is we want to link this VS Code and with our virtual environment. Okay, so what's the name of our virtual environment again? So it is Atal. So this is our virtual environment. Okay, we want to link this or map this to our VS Code. Okay, so that whatever packages that we have installed or will be installing after this inside this environment will also be visible in this VS Code. Okay, so if we want to do that, we should click. Okay, so Control Shift and P. Okay, at the same time, Control Shift P. Okay, Control Shift P, you will be having this Python select interpreter. Okay, if you cannot see this, okay, so you should install the Python inside the VS Code first. Okay, then you will find this Python select interpreter. Okay. Okay, so again, so Control Shift P. Okay, so we can select interpreter. And then what I want to do next is I want to find our virtual environment name, okay, which is Atal. Okay. Okay, so if I have choose that, now I have confirmed that I can also run PyTorch inside my in my VS Code. Okay. Okay. Now we have finished on the preparation of our tools. Okay. Hopefully. All right. Now we are ready to run our YOLO. Okay. So let's go back to our Ultralytics. Okay. All right. So if you scroll a little bit to this Ultralytics, okay. So you should see this. Sorry. Okay. So first you can see this use Ultralytics with CLI. So that's the first one. So the second one, if you scroll down a little bit more, you will find use Ultralytics with Python. Okay, there are two ways to run this Ultralytics or YOLO. Okay. Okay, so let's try the first one first. Okay, so the first one is what we call as CLI, command line interface, CLI, meaning that we can run directly our YOLO on our command prompt. So you can copy here, or you can just click this to copy. And then you can go, we can run on this Anaconda prompt, or we can run on our VS Code. Okay, so of course, for simple application, you can run on your command prompt. But if you want to, let's say you want to do several other things, when you have developed your project, most probably you want to run on your VS Code as the Python, using Python script. Okay, we'll see after this. But first, let's run our YOLO on this Anaconda prompt first. Okay, so I've already pasted the command on our command prompt here. Okay, so where I got this, where I just copy this. Okay, I just copy this line and then I just paste it on my Anaconda prompt. Okay, so what it says, so we have a YOLO predict. Okay, so what meaning that we want to use YOLO and we want to do the prediction. Okay, there's also you can also train the YOLO, but now we just want to predict. We want just to run the model in one go. And then we need to also specify what model that we want to use. Okay, in our case, if you see here, it is it says that YOLO 11n dash seg. So this meaning that it will use the segmentation model, which is not the one that we want to use. Segmentation will be covered by another speaker, I think tomorrow. Okay, so if you want to do the object detection instead of segmentation, we should get rid, or we should remove this seg, the dash seg. Okay. All right. So meaning that our model now equals to YOLO 11n.pt. Okay. .pt meaning that it is a model file for PyTorch. PT is PyTorch. Okay. So YOLO 11n, yn, that one we will discuss later. Okay. But right now we just run. So source, we can also specify the source. Okay. In this case, the source is a YouTube video. Let's say because I have already my video here, right? So let's say I want to run on my, where is my video? Okay, so I have several videos here. So let's say I want to run on this image first, image. So let's say Ronaldo.jpg. Okay, this is my image, Ronaldo.jpg. So I should change the source here. Okay. Okay, so just remove. I should put here Ronaldo.jpg. Okay, of course I in string with this apostrophe. Image size equals to 320. So this is optional. So if you don't want to, if you want to remove this, also can. Okay, for example, and then you can just press enter. Okay, press enter to run YOLO. on Ronaldo.jpg. So because this is the first time we are running YOLO11n.pt, it will download that model first from the website. Okay, it says here I'm running on CUDA machines. Okay. Oh, so now, what happened here? Okay, so there's a problem. Okay, so probably the name is not correct. Probably this name is not correct. Ronaldo.jpg. I think it's already correct. Let me see the properties. Okay. .jpg, yes, Ronaldo.jpg. Let's run it again. Is it with this or not? I'm not sure. So probably just try to run again. I think probably my installation is got problem here. Okay, so let's try other source first. Okay, so let's run on the, let's say, bikes. Okay, so bikes dot mp4, bikes.mp4. So bikes.mp4. Let's try to run. Yeah, definitely my installation is not successful. I think because it has error. Never mind. Probably I just changed my environment to other environment that I've tried before this. So I can just change my environment like this. So Conda deactivate. So I will go out from my virtual environment, and then I can choose other environments. So I can find my other environments by put this conva environment list. Probably I choose one of them. Probably this one, MV 2024. This is for my undergraduate class. Hopefully it works. Okay, so we need to activate again. So Conda activate MV 2024. All right, so now I'm in this environment. So now let me try to run this again. Okay, so let's try on Ronaldo first. Hopefully it works in this environment. So this is normal things. So if you have error, don't worry. Okay, because yeah. So now it's successful. So it's already run, and the results is saved to this runs detects predict for. Okay, so when it's already run, so we will have this new folder. Okay, detect predict. Oh, we have several run. Okay, so now you can see here it's already detecting the Ronaldo person. Okay, so let's say we run the video. Let's try to run the video. What was the name again? Bikes dot. Okay, so bikes.mp4. All right, so I forgot. So if you want to actually see directly, so you can add another argument, which is show equals to true. Okay, true with the capital T. Okay, and probably just run this again. So this one should run on that video. Bikes dot. Yeah, so now it's running on my video. So it's detecting this person's bikes, and then also the traffic lights, right? And yeah, it's quite quite fast. Okay. Okay. Right. So you can see also the class of the bounding box as well as the value there. So let's run this again. Just want to make sure that you understand. So not only the class, it will also give another value, which is for example here 0.9, 0.89. What is this? This is the confidence score of the classification. So meaning that how confident is the model that it is a person. Okay, so meaning that if it is 0.9, meaning that it is 90% confident that it is a bike, it is a traffic light, and so on. Okay, where is the other 10%? 10% it predicts other things. Okay, so it's not 100% sure, but it is 90% sure. Okay. All right. So that's how you run YOLO on your machines. Okay. Is there any problem regarding this? Most probably you cannot follow step by step, but hopefully you can take note as Dr. I've mentioned just now, and try by yourself. Okay, try by yourself. Okay, to set up the environment first. Okay, and then try to run on this Anaconda prompt. Okay, all right. That's for the running on CLI. Okay, we have some 8 more minutes. Okay, looks like the times has gone really fast. Okay, all right. So now we want to run in the Python. Okay, so if you scroll down, you can see some examples of the Python. Okay, of course you can run this on the VS Code, but we want to have the the examples that can run directly on our, for example, on our webcam. Okay. Before that, let's run on our webcam first. Just want to try. Okay, so this source also can run on our webcam. So just change the source to 0. Commonly it's 0. 0 is denoting the the camera pin of your in your computer. Okay, so if I run this, it should run on my using my webcam. Okay, as the input. Okay, success. Oh, looks like it's just black. Let me see again. Probably it's not 0. Probably 1. Okay, because I've running several things at the moment. Okay, probably the Meet also use my camera. Okay, yeah, I think Meet is using my camera. That's why I cannot run the camera. Otherwise, you can run by yourself. You can put it as camera 1 or 0. Sorry, camera 0 or camera 1. Okay, so let me try on source 2 first, if we can. Or probably I can, probably I can stop my camera. Probably I can stop my camera in my Google Meet. Okay, and then try to run again. Sorry, and then try to run again. I think source 1.
Take 0, sir.
Let me try because I have several other cameras as well. Yeah. Now it's running. Okay. Yeah. So camera 0. Okay. So if you take camera 0, it will run on your webcam. Okay. So for example, person. Okay. For example, if I have a cup, it should detect the cup. Okay. Of course, it's not very accurate. Okay, because we use the smallest version of the YOLO. Okay, cup, right? Okay, so for example, cell phone, right? A cell phone. Okay, Is there any for watch? No, probably not. Okay, so mouse. We don't have mouse as well. Okay. Okay, so that's how you run on your camera. Okay, so okay, why some objects it cannot detect? Because okay, this is why, because YOLO and many more object detection models were trained on a on a data set called Coco dataset. Okay, this Coco dataset only has some 300 classes. Okay, of course, well, you know, the all the classes that can be detected is inside the Coco. So if there is other objects that cannot be detected directly by the YOLO, then we will need to do the custom training. Okay, we need to train. Okay, we need to train the YOLO, okay, on that new object that is not available in the data set. Okay, so that inshallah we will do that probably in the next class, because we are running out of time. I thought I can make it, but wow, the time really flies, huh? Really flies. Okay, okay. Is there any question? If not, possibly we take one or two questions and then we adjourn our session. Okay. Enjoy playing with ultralight. Yeah. After this, you can play around. You can explore by yourself. Okay. That's actually my intention. So I won't cover everything. I just give you, you know, a stepping stone for you where you can start, and then after this, of course, you can explore by yourself, and then grow from there. Okay. Can you give the command of YOLO that you were executing? Okay, that command I just actually you can go to the Ultralytics, okay, directly, and then you can go to the quick start, okay, where in the quick start we start with the pip install, okay, and then we install the PyTorch as well, and then in this part use Ultralytics with CLI, okay, I just copy all of this and then change this model. Instead of YOLO 11N dash sec, I remove the dash sec, okay, and then I just run. So and then of course I change the source as well. Okay, so therefore starting starting tomorrow, I will cover on the how do we train the model, to detect other objects that is not in the Coco dataset. Okay, for example, whatever, for example, mouse, or you want to detect what perfume or whatever that is not available in that 300 categories in the dataset, we will need to train a new model that we will cover tomorrow. Okay, using of course, we will start by doing the labeling, the annotation, and then we will proceed with the training of the model. Okay, I think that's pretty much what I want to discuss. I want to cover a lot more actually today, but looks like my time management is not very good today. Okay, hopefully I can cover more in the next. Okay, so by then, thank you everyone for your attention. We see you again in the next session. Over to you, to the chairperson. Thank you. See you again.
गाड़ी काट रहा है family.
Thank you, sir, for your wonderful and interesting session on uh, object detection.
Can you unmute, please?
Okay. Thank you, Dr. Hasan, for your wonderful session and interesting session on object detection. So I request all the participants to kindly fill the feedback link, and meanwhile, the next session will start.